All right, we're recording. That's good. Third try is the charm. Third time's the charm. So we're kind of shifting gears here, and we're going to be doing a lot of the same things now that we've already learned, but we're going to be doing it in a slightly different context, okay? So we're learning kind of like structure, not skills. We're going to be talking about parametric now calculus, which is closely related to vector calculus. And parametrics is really a teak of pre-calculus, but there's so many teaks in pre-cal, we don't really have a chance to get to parametrics. And it used to be an algebra 2 teak, but not anymore. So what is parametric? Well, what is a parameter? That's the root word. What comes to mind when we say parameter? Guideline. That'd be perimeter. Parameter would be a guideline. I like that word. It's a guideline. Okay? You have to work within the given parameters, okay, within these given guidelines. So mathematically, the guideline is going to be like this third-party official that keeps track of the X's and Y's, what they're doing, all right? And here's a real simple example. Let's say you're in a physics class and you take a chip shot with a golf club and a golf ball. You can measure the height of the golf ball against the horizontal distance, D, that it travels, okay? This might be measured in feet. This might be measured in feet. And if that is what you're measuring, then the path of the ball might look like that, and that's actually a pretty nice description of what the ball is doing, okay? It's going out to the right as it goes up and comes down. So that's one way to graph things. But what is a better way to do that is, let's say I wanted to isolate those two distances. In other words, I wanted to figure out not where the height is as a function of how far it's traveled, but I want to figure out what is the height that the ball travels as a function of time, t, and then what is the horizontal distance that it travels as a function of time, t. We would then split these things up, okay? And that's what parametrics does. It takes something that is maybe y equals something in terms of x, and it splits it into two separate functions that are connected by a parameter, which is typically t. Time makes the ultimate independent variable and becomes really the ultimate parameter. But you could choose any arbitrary variable to be the parameter. All right, so let's look at example 1. We'll just kind of try it out. It says, without a calculator, make a table and sketch the curve indicating the direction of your graph. Then eliminate the parameter, verify on your calculator. So here you go. We have a set of what we call parametric equations. It takes two equations now for a graph. You have the x-coordinate now as a dependent function of time t, and you have the y-coordinate now as a dependent function of the independent parameter t. All right, so it's kind of like we're splitting up the horizontal distance of the golf ball as a function of time, and the vertical height of the golf ball as a function of time. Now over here, there's a little window, and you can think of t in terms of time. It's kind of helpful to think about it in terms of chronological order. We have time values from -2 to 3. So what I want to do is figure out what does the graph look like in the coordinate plane. When I'm graphing this, I'm still going to be graphing it as a function of x against y, but I have this third-party variable that relates the two to each other. So here's how we would do it. We're going to make a t-chart, much like we did in Algebra 1. But I'm going to have t values, then x values, then y values. So we're going to have 3 columns instead of just a typical 2. And I'm going to choose values of t over here. It says to start at -2. I'll just choose some nice integer values, so like maybe -1, 0. We're going all the way up to 3, 2, and 3. So that's kind of like your independent variable, but it's independent variable times 2, because it's the independent variable for these two functions. So what I want to do now is see what does the graph look like when I create my ordered pairs. So let's go ahead and fill in. When t is equal to -2, I want to know what x is. How am I going to do that? Plug it in right here. So what is x when time is -2? -2 squared is 4. 4 minus 4 is 0. So you can think of this as at -2 hours on your stopwatch, or like 2 seconds before something starts, The horizontal position is 0. Well, what is y? What's the vertical position at that moment? Well, plug it in here. This says it's what? -1. Now we still have an xy coordinate of 0, -1. So let's plot that. I'll call this, let's call this -1 right here. And I have this dot. So that's still the xy coordinate, but now that happens at t equals 0. So we actually get more information. Okay, we can actually tell when the graph was at that y-intercept and not just that it's there. We get this other dimension. We get this time aspect. All right, let's say 1 second later at t minus 1, I want to know where the object is that's moving. You can say it's a golf ball still or a particle. Where is it at t equals -1? Well, again, same idea. Plug it in. You get x is what? -3. So again, thinking in terms of time, what we could say is in that 1 second, this object or whatever that's maybe moving through the coordinate plane went to the left 3 units from 0 to -3. And what would be the new y value at -1? -1/2. And while it went left 3 units, it went up a ½ unit. Okay? So I have another ordered pair that I can plot. -3, I'm just going to call this -3. And it's going to be -1/2. Let me extend this out a little bit. So -1/2, let me put my -3 smaller. To sketch -1/2, it's going to be right around here. So I'll just label that as -3. So what's happened here is the object didn't actually go straight up a ½ unit and then directly to the left 3 units. What it's doing, if we were to choose more points, we could actually see it better. It's moving from one point to the next kind of along a curved path. And we're just kind of taking a pulse at different values of time. So this would be at t equals, I put 0 over here, but that's not right. That's where we started. I'm sorry. It was t equals -2. It would be t equals -1. We're still counting by 1 second intervals. All right, so another second later, now at t equals 0, let's figure out what the xy coordinate is. What is x? -4, and y is 0. So again, in that next second, from -1 to 0, the object went to the left, not 3 units, but only 1. So now you get this idea of speed, don't you? As this object maybe is moving to the left horizontally, it's slowing down. Can you see that? It went 3 units in 1 second and only 1 unit in the next second. What is it doing vertically? It went up another ½ unit. So this thing is actually moving vertically kind of at a constant pace. Well, I'm just going to draw that right there and put a dot. And I'm going to say that that's -4. And that happens now at t equals 0. So I could tell that this object or this particle, I'll call it particle from here on out. It started here at t equals -2, and it appears to be moving to the left and up. Do you agree? And I know exactly when it's at these coordinates. All right, continuing the process. When t is 1, I plug it in, and I get -3 for the x and 1/2 for the y. So now it's gone back to -3, and it's up at +1/2. So that should be right around there. So notice what has it done in that next second. Yeah, it's changed horizontal directions. It went from moving towards the left now to moving back towards the right. But vertically, it didn't change directions, right? It's still moving upward, which appears to be at a constant rate. At 2, let's see where it's at. Let me finish labeling that. T equals 1. Okay, so at t equals 2 seconds, which is actually 4 seconds after we started, we get 0 and 1. So now it's back up here. That's at t equals 2. Yeah, if you put the t values, it does get a little messy. Now notice that it appears to be kind of accelerating again, but this time in the positive direction. Because when it turned the corner, it took 1 second to go 1 unit to the right, and now in the next second, it's traveled another 3 units. Okay, but it still went up at a steady pace of 1/2 unit. And then finally, where our parameter value, time ends at 3, we'll plug it in, and we get 9 minus 4 is 5, and 3/2, 1.5. So now I'm going to come way out here, call this 5, and it went all the way up to 3 halves. Okay, so that'll be, I'll just finish it like this, maybe right there. And there you go. Now here's what parametric does. It's really, really cool. It gives you more information. Because if you look at something in the XY plane, or as we're going to call rectangular coordinates, just X and Y, you can tell by the shape of the graph the path of something that's maybe moving. Okay? So think of this as being like tracks in the snow. If you just looked at this graph, you might see these tracks in the snow. But let's say it's made with like skids, so you don't even see feet. You could tell the path the object traveled through the coordinate plane, but you'd have no idea just by looking at, a single line in the snow if the object that made that path traveled, from low to high, or if it traveled from high to low. You wouldn't be able to tell, and you certainly wouldn't be able to tell how quickly it traveled along that path, would you? So rectangular or XY coordinates give you what's going to become the path of an object through a two-dimensional space. What parametrics do is a lot more. They certainly give you the path. You're still going to trace out the graph in the XY plane, but they give you 2 more pieces of information. They give you what? They give you the direction, because we're starting at, the small value of t. So now we know for sure from the parametric side that this thing started at the bottom and ended up at the top. So we get the direction it was traced out, not just the path, and we also get the what? The speed. We get the speed at which it was traced out. Okay? And that's where the calculus comes in. Because if you think about this moving from left to right, it's kind of decelerating as it makes its way to turn the corner, and then it accelerates going back to the right. And anytime we're talking about a rate of change of something that's a variable, we need calculus to do that. So this is very intimately related to vector calculus. Okay? You have kind of your horizontal component, your horizontal position, your horizontal velocity, and then you have your vertical position, vertical velocity, and even vertical acceleration. But the path of the object is not really going to be traveling specifically left and up. It's traveling along a curved path. But we can still break it down into what we called in physics, or which I called in physics, the component vectors. Right? Did y'all do that? Yeah. Okay. So that's all parametric calculus is. It breaks down the path of an object into its x and y components in terms of a third-party variable t. So that's cool. You kind of have a nice intro to parametrics. When you get back from lunch, we're going to sketch it on the calculator, and we're going to let the calculator sketch it out for us in one smooth line. And then we're going to graph the other 2 there and see what those look like. And then we'll kind of summarize here. And then we'll probably do one more example and then get to the calculus part, hopefully today. But today, if we just focus on the non-calculus part, what is parametrics? Let's get the mechanism down, and then we'll do calculus maybe on Tuesday when I get back. So, all right, we'll stop there for now. Have a good lunch. We'll see you when you return.